Yes, my name is Hans-Peter Selasky, and I'm from Norway, and I'm a master in technology, in information and communication technology at the Agder University College, Faculty of Engineering and Science. During the last 5, 6, 8 years, I've been spending some of my spare time on improving and now in the end making a new USB stack for FreeBSD-8 and 9. This presentation I will go through some of the insides in the USB stack. Probably you all know what the USB plug is, but you maybe don't know exactly what it is technically. I'm not going to be too technical. I'm going a little bit into technical details to give you an impression how USB works. I'm going to try to stay high level as much as I can, and I'm not going into all aspects of the new USB stack. I'm only going to talk about certain selected aspects. So first, I will have an introduction. Many operations on USB involve transferring data, and that's very important. I will talk about SMP. SMP was one of the reasons I started working on the USB stack in FreeBSD. I had written a device driver which depended on a SMP-enabled USB API. And at the time I started working on the USB stack, there was just a single giant lock around the whole USB stack. I'll also talk about some features in the USB stack. What happens when there is a panic? Can you use USB when there is a panic? I will also talk a little bit about USB in user space. That's evolved a lot recently, and last year we had a Google Summer of Code project with a student from France, Sylvester Gallon, and he was doing a good job in user space on FreeBSD in USB regard. And in the end, I will talk a little bit about the history and some lessons learned. What is USB? I'm not going to say too much about the electrical details, but USB has 4 wires total. 2 wires are used for data communication, and the 2 other wires supply 5-volt electricity, and you can draw up to 500 milliamperes. Sometimes devices connected use this for charging. They have a special mode which you only use for charging. In this presentation, I will not discuss that. I will focus on devices which transfer data, like a memory stick, web camera, mouse, keyboard. There are lots of USB devices. USB is divided into 4 quality of service categories. The most high priority transactions you can do are called isochronous transactions. These are transactions that happen at a fixed interval, and there's no retransmission of the data. Then you have so-called interrupt endpoints, and these also have a fixed rate at which they do transactions, but they have retransmission, so it's sort of like TCP for the IP-interested people. Then you have control transactions. These are a bit special, and in the end you have bulk. That is often used for memory sticks because it can transfer a lot of data and it eats up the remaining bandwidth on the USB bus. You can read more about USB at www.usb.org if you're interested. There's a lot of PDFs there, and specifications can be downloaded. The API I've created is very simple, in my opinion. You have two sets of functions. You have blocking calls and non-blocking calls. The reason that I did this is because I want to isolate allocation of memory to the time when you attach the driver. I don't want that my driver allocates some chunk of memory for signals or messages during operation, because this slows down the system a lot. I'm going to read a little bit from an email I got from Bernd Walter in Germany. He was writing in 2008 in November that the latency of the new USB stack is so much better that I really can't believe. And then I hacked diff attached the U-modem driver to attach to the CDC device. This is not the correct way to do, but it works good enough for me. After I had a dev CUA/UX, I could flash the 1891 SAM 7X256 using the new USB stack. You see, this took 28 seconds to complete. With the old stack, it took 15 minutes. The protocol used is quite inefficient, since it transfers 4 bytes payload, waits for a response, and then does the next 4 bytes. So practical results show that if you try to do something like a malloc, even if it's non-blocking, inside one of this starting and stopping transfers, and these are done frequently enough, it's going to kill performance. So instead, you should allocate whatever you need at attach. So you have the memory, and this gives reduced execution latency and reduced CPU usage. So don't think about your coffee cup, that you can set off a flash or something in the background and it takes a lot of time, and now I have a reason to have a coffee. So this using the USB stack can be a little bit dangerous in that regard. In the top here, there's actually a new feature described. This API, which is described here with 5 function calls, is actually symmetric. Before, there was only host support. Host is the PC usually. It can also be an embedded device, which is host, but the host is usually the PC. The other side, device mode, is when you try to emulate something like a mouse. It can be a flash stick. It can be a memory device, CD-ROM, USB CD-ROM. When you try to emulate or emulate such device, you're in device mode. And this is quite genuine, because on other operating systems like Linux, you have 2 different stacks. You have one stack for host only and one stack for a gadget, is what I call it in Linux. And what's the reason to have 2 different APIs to transfer buffers? It's just duplicating code in the kernel. So really, there's no use, and they actually admitted, Linux developers, that yes, they maybe should join these 2 stacks as well, but it looks like this time I was the first one to do it, actually. USB transfer drain. I'm not going to say so much about these functions, what they do. You can read in the man page of USB stack in the FreeBSD operating system. There you will find a long description describing what all its functions do. Yeah. USB is packet-based. It's not IP packets we're talking about, but they use HDLC bit stuffing to send data across the USB bus. One problem about USB is that there is no way to say this is the last packet. It's actually just a serial stream, like in the word USB, Universal Serial Bus. So how can you get any performance on a serial device? You might think /dev TTY, can I transfer 50 megabytes per second on /dev TTY? No, maybe not. So what they invented after a while of USB protocol implementations is a technique where they send a so-called short packet. That means that you define some fixed size which you transfer when it's not end, and when it's end you send a short packet or zero-length packet, which is illustrated in the figure. And that is what you call a USB frame. So a USB frame can, for example, consist of Ethernet packet. So Ethernet packet will be split into multiple USB packets, and then a short transfer in the end, and then it's transmitted, and then the receiver understands at this point the transfer ends, and after that we start a new transfer. It's a way to synchronize framing. As you can see, there is a number here. Number 0, number 1, number 2, number 3. The new USB stack is IO vectored. You might know that the read call in libc, there is also a vectored version of read. So you can read into multiple buffers having different lengths. And this is very useful because there is a problem with USB that you need to wait for an interrupt until a transaction completes. And there aren't so many interrupts coming per second. It's like from 1,000 to 8,000 interrupts per second. And if you're not able to send enough data in a single USB frame in 125 microseconds, then you will not fill the USB bus with activity. So that's why you can now transmit and receive multiple USB frames at different memory locations in the same USB transfer, which is indicated here. Yeah. Maybe some of you here were at Cambridge last year, and Robert Watson, he showed you a traffic sign which told about some new technology created by Apple. So I'm going to show you a double traffic sign, but it's not directly related to what Robert Watson was talking about, but maybe you will remember this double traffic sign. It means that USB approximately has 6 internal wait states in the stack. When you start a transfer, this is a USB technical term I have not explained yet. This is called stalling. It's kind of like an error state where you try to recover. You can tell a transfer that it should stay in the stall state until it receives an OK from the other side. This is a new feature. Other operating systems, you have to handle this inside your driver. And my experience from FreeBSD is that almost everyone that tried to do some error recovery did it wrong. They did like synchronous function calls inside asynchronous callbacks, and it was horrible. You also have a new possibility, and that is to nice a USB transfer. It's almost like traffic shaping in network regard. Very many products use so-called bulk transfers, and these just will eat up whatever they get of bandwidth. And this nicing functionality is just a timer which inserts a small delay before the transfer is started. And that way you can give priority to different USB devices depending on what the user wants. This is also something new. You don't find it in any other USB stacks I've seen up to date, both open and commercial. After nicing, you resolve physical addresses. It's short for bus DMA. I'm not going into any details there. Then you have two functions actually which sound similar. You have enter and start. Enter is called before start. Enter has to do with double buffering, that you can submit a transfer to hardware before it's actually started. Start is when the last transaction on a so-called USB endpoint. I have not explained that either, but there are multiple FIFOs in USB. So I'm not going to explain that very much right now. So first you have the enter to kind of give, if your hardware supports it, you can submit the transfer into hardware, so you get pure double buffering. If you only do submit it in the start, you will have single buffering, and this affects performance. So that's why there are two ways to submit the transfer. Also something new is that you always get a done callback. If you submitted something down, you will always get a done callback. And it's worth noting that this submit function does not have a return value. It's not indicated in the slide, but the transfer submit does not have a return value. So that means it won't fail, but you can get a callback with a fail code. And then you can do a stall, which will introduce some delay and start again. So I kind of thought through a way you don't get the system off hook suddenly because you have an error. Yeah. Something new here is to split control transactions. It's very common that you need to allocate a memory buffer that contains the whole request first. And hence control transfers can transfer up to 64 kilobytes. You don't want to allocate that big buffer for every USB device. So I introduced a new state to split control transactions into smaller buffers. This is more technical stuff. It's yeah. A new feature too is to, via this splitting, you can now copy data directly from user space to kernel when you're doing a control request. That also has a speed up gain, which I was telling you earlier, that the latency has been much better with control transfers. And this is also one reason that instead of doing a malloc, that I malloc a kernel buffer, copy it in, or do a mem copy in the kernel, and then do the transfer, and then copy out and free the buffer. I just have copy in. So it's much faster with small transactions and also big ones. Yeah. Hence, the USB stack is SMP safe. I've added a mutex argument pointer to several USB functions, so that whenever the USB stack sleeps in synchronous functions, it will exit a mutex. It's mostly for convenience. USB stack at SMP. I tried to make a sane locking layout. DCHC, that's device controller, host controller. This part of the code is protected by one lock. Then you have your class driver. It can be a device class driver or host class driver, because the new USB stack is symmetric. It has also one lock. Uh, so the device class driver lock is locked first, and then the host controller, device controller lock is locked. So actually, it's not like this that you unlock the driver lock and then you call a function to do something in the device or host controller code. This is because that you cannot make an operation atomic if you need to drop the lock. And this has been very important to me, that you can start several USB transfers atomically, and you can stop them atomically, and it makes design easier of a driver that when you're stopping a transfer, it can be in connection to tearing down an internet interface, Ethernet interface, for example. Then you stop the transfers that receive data atomically as you tell the network interface is down. It has a limitation that one CPU can only work at one DCHC at a time. It's not possible that two CPUs can do anything in parallel on this DCHC. However, the drivers, there is a possibility that they can do things in parallel, but whenever a driver calls into the DC or HC, then it's serialized. To avoid problems with mutex collisions on a thread, that you have that we don't mix callbacks that lock giant with callbacks that lock non-giant mutexes, I've created several threads so that device controller, host controller will spread callbacks on several threads. And this is, of course, improving performance. And this illustration just shows that you have two mutexes, and there are 4 lock combinations regarding to locked, unlocked, and that's enough. I've tried to build in as much locking, unlocking operations as possible into the USB API. For example, when you get a callback, the mutex of your driver is already locked, and the reference count handling code and logic associated with draining a USB transfer is integrated in the USB stack. My idea is that this should resolve corner cases. What happens if blah, blah, blah? There are a lot of corner cases. So the idea is you run code atomically with regard to a mutex, and maybe someone of you will disagree with me that you shouldn't run lots of code under the mutex, but that's the way you do it in USB to have a simple logic with regard to locking, unlocking, and avoiding problems. Another technique to avoid problems during detach is to refer transfers by a pointer. So actually you have an array of pointers, and you reference this pointer under the private lock of the driver. And also the private lock is locked when this is cleared. Therefore this transfer, start, stop, there are many more checks for a null pointer, and will return if there's a null pointer. And this is just a small detail regarding to detach, why it's done like that. Yeah, I've already said that. Something new which many other FreeBSD developers didn't understand in the beginning is why do I need my own callback thread system? Why can't we use the task queue? Well, I have a requirement in the USB stack that the last queued job is executed last. And a task queue does not guarantee this. Look, take for example this following illustration. The first line shows what the queue looks like initially. You have a command that's switch on, and it's queued 2 times, so it 2 times switch on. Then you have something else switch off, and some other command, and the second. Okay. So the second line shows what happens after you try to queue the switch on command again. And what happens then is that there's some code that figures out which command was queued last, and then it takes that command and puts it at the end of the queue while keeping the first queued command in the beginning. And this ensures that the last queued command is executed last. The problem about the task queue solution is that if I would use a task queue, then the pending count would just increment and the command would stay at the same place in the queue. So it would be a problem. Of course, if I were to use a FIFO with infinite number of commands, then that would be the solution. But then you use more memory. And I want to be smart and try to make some simple building blocks that reduce the need for memory and kind of join command events in a smarter way. This slide shows a little bit about the device organization. USB always has a root hub on top. You have different ports. The root hub has no parent. And then you can have a sub-hub, and this can have different ports again. Different kind of events like probe, attach, detach, suspend, resume, shutdown are going downwards in the figure. Yes. So that's how USB devices are organized in the USB stack. And also this is valid for other USB stacks. Power save, that's something new in FreeBSD. Power save is integrated in the root hub code. There is currently a 30-second timeout, and it will enable power saving functionality. By default, it's only enabled for USB hubs. You can turn it on by using USB config. The reason it's turned off is that many USB devices are broken. That means if you try to enable it, your device might disappear suddenly and never return unless you manually replug it, and that would be a bad user experience. So that's why it's turned off by default. During my design, I added a new status bit to the USB specification. This bit allows you to distinguish between host and device mode, and probably I'm going to pursue it so I get this into the standard one day, because the original USB design was that the host should have nothing to do with the device and the device should have nothing to do with the host. It's like two different pieces of code. That was what the designers of USB thought, and I disagree a little bit with them about that. USB stack in polled mode. Polled mode is a special function that you can call on a transfer. It's used during panic time. So maybe you've noticed, but actually the USB keyboard works in KDB. And how come that the USB keyboard can work in KDB? Well, it always worked in KDB. But if you look in other systems, that's not a natural thing. And the reason that works is that there is a special mode where you can poll if there is transferred data on a USB so-called endpoint, which I showed in the early beginning of the slides, like control transfers, bulk, interrupt, isochronous. You can also dump data to a mass storage device from KDB, which is of USB kind. And you can also use the USB keyboard if it's enumerated at mount root. This polled mode adds a little bit complexity to the USB code. The most problem is in the keyboard driver itself, because of a little bit confusing APIs during boot up, that at some point you should return events to, or keyboard presses to one function, and the other mode you return to another function. So it's a little bit difficult, and it might be that if you're unlucky the keyboard won't work, but that's like 99 to 1 that it will happen. So usually the USB stack should work at panic time. USB and user space. I would like to thank Sylvester Galland in France for helping out writing version 1.0 of libUSB for FreeBSD. These libUSB APIs were added in 2009, I think, last summer. And it allows you to use Linux user space applications in FreeBSD. You can also think like this, that this allows you to also use VirtualBox, potentially seamless on FreeBSD. libUSB version 1.0 and 0.1 are implemented on top of libUSB version 2.0, which is more BSD specific. The reason I made libUSB version 2.0 is because I needed an API that directly reflect the kernel functions of the new USB stack, so that I have all the functionality available. Most of the functionality which I provide in the kernel is available in user space. Also, there is support for legacy endpoint nodes. That's /dev-ugan, so you can cut and echo on a standard endpoint if you need that. The layout looks like this. You have the USB kernel, you have /dev-USB, and you have one handle which transfer all endpoint traffic. Then you have the libUSB abstraction, and then you have your application. If you want your application to be portable, you should use libUSB version 0.1 or libUSB version 1.0. If you want to bind your application to FreeBSD, you can use version 2.0. To configure the USB stack, there is a utility called USB config. This utility can do things like selecting USB configuration. A USB device can have multiple configurations. It can, in one configuration, be a mass storage device. In another configuration, it can be a modem. It's like a description of itself. USB config can also dump USB descriptors. It can manage USB quirks. It can perform USB control requests, and it can select USB power mode, and many more things which I have not listed in this brief presentation. USB config, in other words, is your Swiss Army knife to do something on USB without having to compile an application. Also, a new feature in the USB stack is what I've called a USB mass storage tester. Nowadays, many manufacturers of gadgets, that they have an auto-install disk, which is designed for a system I won't mention here, but it does obviously not work on FreeBSD. So I've added some automagic code to figure out if USB gadget is in this mode, and then just kind of eject this medium or try another configuration which is supported. A good example of this is 3G dongles. There are a bunch of them and bunch of different vendors, and they do it differently, and they all think that you should just plug it in, it installs something on your computer, and then it works. So that's their idea, and just recently they started to think about other operating systems, like putting maybe a shell script for Linux, and BSD is usually not mentioned, but that's the fact right now. So I had a specific test to get rid of that. USB throughput and performance. Well, nothing more and nothing less than what the others do. However, there are some limitations that you need to think about if you want to design a USB application. Typically, full-speed hardware does not have more than 1,000 interrupts per second. Translated, you can't submit more than 1,000 bulk requests per second, even if you have a while one loop without delay. So this is something you need to consider when you design your application. High speed is 8 times more frequent. Still, it's not enough if you have a small amount of data which you transfer. Throughput range from around 0.8 megabytes per second for USB 1.0 to 35 to maybe up to 40 megabytes per second for USB 2.0. These numbers depends a lot on your hardware. And here are some numbers I extracted just before I came to this conference. This test is frequently used to measure performance. It's reading data from a USB disk. The results show that actually on a MacBook Pro, the FreeBSD USB stack does not perform so well. It's actually doing 60% of the generic Mac and Linux on this MacBook. However, if I use exactly the same USB code on another chipset, I get actually more throughput than on both of or all the three other tests. So how come this be? This has something to do about the hardware, and what I found out during development is that different manufactured hardware behaves differently, and sometimes there are bugs in the hardware. And for the time being, I'm trying to get some overview which bugs can be fixed and which chipsets are affected. So far, no one has really complained that the throughput went down, but this test just shows that you might be unlucky with the choice of hardware, and you can get through bad throughput. But it doesn't mean that there is a problem in the USB stack itself. It's usually a hardware problem. Security and reliability. I've specifically spent extra time to identify problems like reading, writing outside buffers. USB has a lot of descriptors, and all these descriptors have a length byte in the beginning, and the variable lengths can cause enormous problems if you don't check things carefully. I've also spent a lot of time to identify races during detach, and for example, in the charter device access part, there's added a lot of code to handle races, so that you're not in code after you unplug the USB stick, and that the memory is not accessed after you unplugged it. To sum up, some history and lessons learned. All of this started in 1999 when I was 17 years old. I had some piece of hardware, it didn't work, but I had a data sheet, fortunately. So I made a driver, and then I found out all the problems. And then I started to do something about it. And most of development was done when I was going to Agder University for 5 years. After I did my homework, I spent a lot of time on programming on FreeBSD. I also want to use this opportunity to thank the FreeBSD committers and core team for giving me the trust to make a new USB stack in FreeBSD. It's been a challenge, and I hope that they're satisfied about my work, and also you. And I also hope that my work will inspire people for many years to come. So, are there any questions?
Hi. Are you planning to add support for USB 3.0?
Yes, I'm planning it for this autumn.
Okay, thanks.
Another questions?
What about wireless USB?
We have all the definitions for wireless USB, but so far someone needs to volunteer to write the daemons that handle mostly encryption-related parts, because wireless USB has a lot of encryption in it, and someone has to volunteer to do that work. It's some work.
Have you created a wiki that has a list of tasks for that?
No, no.
It would be helpful, probably.
Yes,
just as a
thank you.
suggestion. The second question, and maybe it's too technical for this. I have some questions about DMA and caches and stuff. Are you going to be around later so we can talk?
Yes, I will be around, and I'm more than happy to talk about my USB stack.
Finally, just thank you for making the stack usable again. I can make DVDs, and I wasn't able to do that with the old stack, so it's really nice. Thank you.
You're welcome.
Other questions? So if not, oh, I'm sorry.
Do you have support for split transaction when working with USB 1.1 devices?
Yes, we have pretty good support for high speed to full speed split transactions, yes. But I had to do some compromises. So if you transfer too much data in each USB packet for asynchronous traffic, there might be a problem, but that can be fixed. I would say that's not my problem. It's due to bad hardware design for this kind of thing.
Maybe you want to try your USB stack on latest Marvell chip with different hardware. Maybe it will be
Yes,
better.
that would be interesting if someone would sponsor some hardware that I can test on. So I'm not saying no to sponsored hardware.
Thank you.
Other questions? Okay, if not, thank you all very much.